So on this page, what we are showing where we are operating. So in this whole sort of supply chain integrity, our activity will be focused on farm to study animal welfare and improve animal productivity. So in this work, we got a few big challenges to address. The first challenge is animal welfare, especially on farm setting. The reason is because typical livestock are social animals. They exhibit certain social hierarchy, and we want to understand their behavior so that we could understand why they become sort of aggressive towards each other, how could they deal with each other in a sort of calm environment so that they could continue to grow as we expected. Another important part of the social behavior, welfare, and hierarchy is by understanding their sort of intrinsic bonding between animals or leadership of animals, we could potentially identify animals which generate most influence or impact on the rest of the group or herd. So this will help us to sort of put correct sensors on correct animals so that reduce the number of sensors to be deployed and also reduce the labor which will associate to maintain the sensors or technologies. Another potential problem or challenge we want to solve is by talking with our agriculture and food colleagues, we realize prolonged labor is a very critical issue across the industry. As we are showing on the pie chart on the right-hand side of my slide, almost half of the animals, half of the lamb sort of died associated with the prolonged labor. So this is a very huge cost of our red meat and the wool industry. So this is definitely a big issue of animal welfare. It's a cost hundreds of millions income lost to our farmers and the industry and the country, and also it causes a substantial reduce of animals which we would expect to achieve. So these two challenges we look at, we believe there's one possible remedy or solution to help improve the welfare or have a human intervention to reduce deaths or lamb mortality caused by prolonged labor. Our solution would be a fine-grained real-time tracking system, which could give a very accurate real-time trajectory, but also offer remote accessibility to the system. By saying remote accessibility, what we mean is we want to develop a digital technology where operator of the farm could have real-time insights on what's happening on the farm, and then they could generate the influence and also make appropriate decisions. So we look at a few scenarios in this research module. One module is a larger open space. How can we track animals accurately in open paddocks, for example? The other one is enclosed areas, because we do experience the situation where so you are giving birth to lambs inside enclosed ponds. So get a very accurate locations where the ewe is so that we can predict or estimate if the ewe is experiencing difficult births. And this could be a very good, useful performance indicator for human intervention. On this page, I illustrated the scenario or the system we developed for the open space, where we rely on a state-of-the-art GPS technologies called real-time kinematic GPS to develop the real-time tracking in open space. So what we are looking at here is different from standard GPS. We have a reference point or reference transmitter receiver. This device gives additional information from the GPS around the oversee the paddock, and calibrate GPS information for which each of the animals tag would provide. Once the GPS information is captured, the GPS information will be transported through 4G network and then into our gateway and the internet all the way to the remote end or customer. In our case, all the data will gather from Armadale to Sydney, where data will be monitored, real-time processed, and the decision will be made. So the benefit of this system is compared to the conventional GPS, we typically look at a few meters to up to 10 meters in accuracy, right? So this inaccuracy would cause significant sort of interruption towards the correct estimation or inferring the trajectory of animals. Well, by using our RTK GPS or collaborated GPS system, we achieve an accuracy to be a sub-meter level. In many cases, it's about a half meter. If the animal remain stationary, we achieve a 25 centimeter accuracy. So this accuracy will be accurate enough for us to build up where the trajectory of individual animal also get a very accurate relative locations between animals. And after having this accuracy, our end goal will be identify the key animal and then only tag those animals for useful applications, for example, virtual fencing. By locate the lead animal, we only want to tag the virtual fencing system around the lead animal to navigate the whole flock or whole herd of the animals. On this page, we are showing the system we created for enclosed areas like a barn. In the middle of this slide, we show the barn we operate in Armadale. And in the left-hand side, we are seeing a flock of sheep or ewe. These are pregnant ewe with the tags we developed. The tags are being developed in this particular experiment as a collar. So on the right-hand side, you see what the collar is. But please note, the electronics part, the localization part is fairly small. If you can see on the white plastic, there's a very smallish, sort of like a finger-size electronics module, which is developed to be animal-proof, weather-proof, and heat-proof. Well, the bulk part of the collar is to secure this device on the back of a sheep and minimize the potential sort of impact to the pregnant ewe. On this page, what we are showing is a comparison study of our technology and the GPS, standard GPS. On the left-hand side is the standard GPS system, and the right-hand side is our system. We look at 10 animals. These are the trajectory from real 10 animals. And what you can see is on the left-hand side, even we got 10 animals with GPS. Actually, from time to time, we only get a subset of the animals' GPS activated correctly because the asynchronous issue and also because a protocol issue inside the GPS system. On the other hand, our system can always get a real-time trajectory of all 10 animals because the collaboration we achieved and also because we use data fusion technologies to fuse multiple sensory modality. The second part...
just giving you a minute warning.
Okay, thanks. We're almost there. The second part, it's important to notice actually on the left-hand side, we get a very accurate trajectory, while the GPS trajectory is not accurate and not useful at this moment for build up the trajectory. So based on the trajectory we get on the previous page, we generate insight. On the left-hand side, you can see a network graph of the animal, 12 animals. And the width of the edge between two animals, dots, indicate how close the particular two animals are during the whole simulation process or experimental process. So we see these few animals are particularly good to each other, while some other animals would remain sort of apart from each other. On the right-hand side, what you're seeing is actually we using data analytics method to map the 10 animal behavior across a few days onto two-dimensional image. And the animal close to each other indicate that they got a certain bonding, while some animals are far away and they are not particularly good with the rest of the group. So this is a good indicator of which animal could be particularly sort of influential in the middle of the flock, even not sort of in the physical world, but in the highly mapped multidimensional world. So this will be the animals, this few, we want to have sensors. So this brings us to the conclusion of our work. We develop a fine-grained real-time tracking system to improve animal welfare and also reduce land mortality. And the different systems developed for different scenarios, and also the system sort of integrated digital technologies and the data analytics, and to help reshape a potential future welfare aspect of farm animals. Thank you. That's the end of my slides.
Thanks, Wei. I've probably got time for just one quick question before we start the next presentation. Lamb mortality, you brought that up at the beginning. It's a huge industry problem, and I think you might have covered it in your final slide. But does this technology work in both our northern extensive systems, so massive properties up north, as well as our southern intensive systems? Can it be deployed in both locations?
This is definitely part of our plan. At this moment, we look at the southern dense system at this moment, but the end goal is to have a cost-effective solution which could be deployed in very wide area, cost-effective, energy-efficient, and sort of robust system. Yeah.
That's great news. We love to be able to make sure we can work in both those environments. Thanks, Wei, for your time.